Welcome to the video on intelligent planning and operation of multi-energy systems. In this video, we will introduce ourselves with the multi-energy systems, we will learn about their main characteristics, and finally, we will discuss the importance of planning and operating them together. Multi-energy systems are energy systems comprised of several energy carriers with the capability of energy conversion between these carriers. The three energy carriers which are most commonly routed through networks are electricity, natural gas, and heat. And their networks can span sizes from local neighborhood level to continent-wide level. While electricity grids are everywhere around us in the developed world, some countries have equally developed complex natural gas grids to supply households with gas for cooking and heating, and industries with gas for heating and as feedstock. Heat networks, on the other hand, can mostly be found in the form of district heating networks in urban areas and as industrial heat networks in industrial clusters. More recently, hydrogen is being increasingly important as energy carrier, as a sustainable replacement for natural gas, and with it, hydrogen infrastructure emerges. The electricity and gas grids are often composed of transmission and distribution networks. The transmission networks are the corridors that connect one part of the country with another, similar to highways, while the distribution networks connect the consumption to the transmission grid. In the case of electricity grids, the transmission grid operates at the voltage of several hundred kilovolts and transfers several thousand megawatts at each moment. The distribution grid operates at the voltage of several tens of kilovolts and transfers amounts of power lower than several megawatts. The losses in the transmission grid are at the level of 5%, while the losses in the distribution grid are higher, in the range of 20%. Natural gas grids at the transmission level operate at the pressures of several tens of bars, and at the distribution level, they operate at the pressure of several bars. The high-temperature heat grids, which are typically district heating grids today, operate at the temperatures below 100 degrees. The natural gas and heat grids have one advantage over the electricity grids, and this advantage is the possibility to store energy in the grid itself. In the natural gas grid, this stored energy is called line pack. The line pack can be of the amount sufficiently high to supply the gas demand of the entire country for several hours, and even sometimes up to a day. In contrast, the energy stored in the electricity grid is negligible, requiring constant balance between electricity generation and demand for electricity. Therefore, we can imagine to use the natural gas or the heat grid for energy storage. In our renewable-rich future, hydrogen grids will particularly be used for this purpose. To store energy in another form, we must convert it. In multi-energy systems, the energy can be converted from one form to another using specific energy conversion devices. These devices include heat pumps for conversion of electricity to heat, gas boilers for conversion of gas to heat, combined heat and power plants, CHP plants, for conversion of natural gas to electricity and heat. In the future, hydrogen grids will be equipped by electrolyzers and fuel cells for conversion of electricity to hydrogen and back. Multi-energy systems are rarely owned and operated by a single organization. Even for a single energy carrier, the transmission and distribution grids are often managed by different entities. Since many parties are usually involved, the planning and operations of such systems must be strongly aligned in order to avoid reliability issues and inefficiencies. When planning the multi-energy systems, what is particularly interesting to look at is the trade-off between various design choices. For example, in an industrial site with several industries, we can choose to place small boilers in each factory, or we can choose to install a single large hot water boiler to produce heat. In the first case, the heat infrastructure is smaller in size, while the gas infrastructure is larger. In the second case, we have a single natural gas pipe coming to the site and many heat pipes stemming out. The case with a single boiler might have the advantage of the economy of scale, but it also creates a single point of failure for all industries around. So it requires commitment from all involved organizations. When designing this system, we must also consider losses in the energy transport and energy conversion, the location of components, if the space is limited, and the permitting requirements for construction and operation. When operating the multi-energy systems, we are particularly interested in aligning the needs of one system with the capabilities of the other. For example, as already mentioned, the electricity grids cannot inherently store energy without the explicit addition of storage elements. On the other hand, the energy can be stored in heat and natural gas grids. Therefore, the natural gas and heat grids can provide complementarity to electricity grids and store some of the green electrons that cannot be consumed immediately. To achieve this, the operating schedules of all systems must be aligned. In conclusion, we have defined the multi-energy systems as the systems of several interconnected energy carriers. We have shown some of their characteristics in terms of nominal operating values and their capability to transfer and store energy. And finally, we have looked at a couple of examples for aligning operations and planning tasks.